This is the lecture for Class 5, GeoData, and this week we'll be taking a look at data in general, what it is, how we use it, and specifically how it resides within a geographic framework. We'll also be taking a look at the raster model. We spent a fair amount of time with the vector model thus far, and we will be getting more familiar with what a raster is and how we can use it. So to get started, let's take a look at Class 4 themes, which we accomplished this past week for map projections. Let's take a look at this video real quick. It's a little bit cheesy on the soundtrack, but it is a good overview of exactly what we were studying this past week.
We live in a three-dimensional world. Everything we see and touch is a three-dimensional object, having a length, width, and height. Our planet is also a 3D object, a sphere. The problem is that most maps are in only 2 dimensions, length and width. Even 3D mapping tools are only simulations. There is no depth. If that's the case, how can the Earth be accurately mapped? With an orange, the skin can be peeled and flattened. Our planet can't be peeled back. Instead, map projections are used for creating maps. How is this done? Features of the 3D Earth are projected onto different shapes, such as cones, cylinders, even flat surfaces or planes, or other shapes. To be successful in GIS, it's important to know about map projections.
Okay, so map projections, we're going from a very complicated space, which is the Earth's crust, into a flat map. And as we do that, we have to go through a series of progressions towards that flat map. And the flat map, one of the things that we gain is very precise measurement. So to do that, we need to get to a mathematically pure surface. And we do that going from the Earth's crust to what we call the geoid, down to what we call ellipsoids or reference ellipsoids. And at that point in time, then we can go out to the flat map. So it's a series, it's a progressive series from a complicated reality into a representation that we can put on a map. And as we do that, we need to be aware that the map that's taking, or excuse me, the math that's taking place behind the map is based on this ellipsoid sphere, that it is an averaged smooth surface in terms of the math behind it. As we go towards our flat map surface, we're tearing, compressing, and shearing in certain locations the original sphere's face, okay, or the original Earth space, which is round. And in those locations, we're getting what we call map distortion. And we want to avoid map distortion as much as possible. We're always going to get some map distortion in any one given map projection, and we need to choose our map projections based on our specific mapping tasks, so we ensure that we're not introducing distortion in the area or across the quality that we're trying to map. And luckily we have a lot of choices. There's lots of map projections, so as soon as we know the typical map projections for the area that we're mapping, or what characteristic that we're trying to preserve, be it area or distance or route, etc., we'll choose a certain map projection. And one of the big gains that we get when we go to a flat map space is we will oftentimes have a projected graticule, and within that projected graticule we're getting planar units. So this becomes really important for any calculation that's based on area. So we want to have actual feet and meters that we can calculate areas with a lot of precision. And on a smooth, round surface, we do well with latitude and longitude points. We oftentimes have trouble with areas, and we get a lot of distortion. And we oftentimes want to go to the projected map space. So the graticules on the sphere space on the left here, those are still an angular, that's still being measured in an angular framework. And we usually want to get out to the projected graticules where we have our x and y on a flat space. And then all of a sudden we have a much more accurate understanding. And we also have planar units, which is great. Now, as we project out to a flat map surface, we're going to use generally 3 basic types of shapes. So we're going to organize the paper around the globe space in 3 different ways. So it would be planar versus conic, the cone, versus a cylinder. Those are the 3 classic shapes that we'll oftentimes use. And where that paper touches the globe, or the rounded space of the Earth, that point of tangency has a lot of accuracy. As soon as we get away from the point of tangency, then we start seeing map distortion taking place. We talked about using UTM, and we actually used UTM for one of our assignments this past week. And as long as our map project is set up within one of those particular zones, we have a high degree of accuracy within that zone across map projection characteristics. So this is a really good choice for areas that don't necessarily have a map projection set up for them. So this is good for remote locations in countries where, as long as your map area was within the UTM zone itself, you'll get a high degree of fidelity. So this week's topic is geodata in general and how we utilize data within a GIS. So we can think of data in general as things that come into a system. In a GIS, we're really dealing with it within a spatial framework. That's the key thing, is that it's there's coordinates that are involved. We're in some type of map projection. We have data that has some connection to our model of the world in a GIS. There's lots of data that are available to us, and we have lots of devices at this point in time that we, quote, access data. And there's this notion that we produce data and that we have data. It's become a really integral part to who we are as individuals. And what's really important is that we now have these relationships with companies, specifically cell phone companies, in relationship to data. And so there's a lot of hype around what data is, and we need to understand exactly what it is and how we can utilize it specifically for GIS analysis. So at its root level, let's think about how a computer actually deals with data. At its root level, it's basically a series of zeros and ones. And we can think of it as a bit versus a byte. So at its really core structural level, we're just talking about on and off, or 0 and a 1, what would be called a Boolean pair at the root level of what data is. So a computer bit, it's either going to be a positive or a negative. It's either going to be an on or an off, and then we string these on and offs together, and then we'll get to a byte, and then we get towards an actual larger piece of data. And the scale and speed by which we're producing all of this data is every 3,000 years of our past history can be produced within 2 days, which is a really amazing thing to think about, that we're producing just that much data based on all the input devices that we have at this point in time. So data itself is not neutral. We think of it as just being, from a computer's perspective, it really is just zeros and ones strung together. But as human beings, data itself is processed in a certain way, and that processing is not neutral. It has a perspective, and oftentimes that's a perspective that comes from an administration or organization, and there's been protocols set up around the data. So we just need to be aware that it's not this thing that is really neutral. Again, from the computer's perspective, it is just zeros and ones, but from our perspective, it has a perspective. And so data does not exist independently of us as human beings. So our ideas, the ways that we set up a context or a knowledge base around data, these can be used to generate and also analyze the data. And this definition is coming from a book that was recently published called The Data Revolution by Rob Kitchen. And he does quite a good job detailing data relative to data systems, and particularly with a nod to geography. So data, it's not random. There's some way of actually collecting the data. We need to always realize that when we're dealing with data sets, that they didn't just appear, that they are developed based on a series of protocols. So oftentimes we're harvesting through some type of measurement. So we're selecting from a sum total of possible data based on a measurement structure. And it doesn't begin with facts or information. We actually use data to create information, and we use data to collect facts. So data is really at the fundamental level of human understanding. We need to have data to move on up a pyramid scale. And with data, we oftentimes use an information system. So we'll be inputting data, we'll be doing something to it. So we'll be organizing it into a database, and then oftentimes we're modeling or doing some type of analysis work, and we'll output the information from there. So this is really classic for GIS, where we input some data set and get it into our GIS in a usable format in a database structure, and then we're going to model and do analysis work on it, and then we'll produce a result that has meaning. So it's gone through kind of a whole series of steps within the GIS to produce a value-added product. So let's kind of talk about what data is in more detail so we understand it. So we can think of it across 5 attributes. We can think of it in terms of its form, structure, source, producer, and its type. Under form, we've already discussed this a bit with thematic mapping. So data is either going to be qualitative, okay, and we know what qualitative thematic mapping is about. It's usually related to a name, and it can also be quantitative, so it can be number-based essentially. And there's 2 types of numbers. There's a discrete breaking of numbers, and then there's also continuous data sets or continuous fields of data. And these are just 1, 2, 3, 4, 5, 6 all the way up to a certain number. And along that continuum, we have lots of collection points. In terms of the structure of data, we have 3 main types. The first one is unstructured data, and a lot of what we experience on a daily basis, say in terms of Twitter or Facebook, these are unstructured data types where there's many different structures that are coming into one stream of information. Now that's very different than structured. Structured is oftentimes going to be in a tabular database format, where somebody has spent a lot of time thinking about the columns and the records, and there's a whole protocol that's set up around how the data is organized and collected. And then under semi-structured, we give some form to the collection process, and it oftentimes is machine readable, but it might not be super user-friendly. It may not be in a database or tabular format that we can easily access and manipulate. So these are the 3 general structure types that we find data to be located. Then we have different sources that we collect the data. So under the sources here, The first one is capture. So oftentimes we'll be using a camera, or in terms of remote sensed imagery, we'll oftentimes use a camera mounted on a satellite. We oftentimes get exhaust data, and exhaust data is secondary to the main purpose. So a classic example is you go to a supermarket and you buy some groceries. You pay for the groceries, but as you pay for the groceries, there's information that's being collected on you as a consumer or as a purchaser, and that secondary collection is what's called the exhaust data. So the main purpose of the transaction is just to simply go in and buy the groceries, but as a result of buying the groceries, some data is produced, and that exhaust data can be utilized. Transient data, the classic example would be like a CCTV camera that's running on a consistent basis, maybe even 24/7, and there's no real protocol that's set up in terms of archiving the imagery. It's just kind of there, and sometimes we might actually use that data, but oftentimes it's just kind of running in the background, and it's only utilized at specific points in time where it's needed. Then the fourth type is deriving. So oftentimes we'll derive data from a particular data method. So in this case, the classic example is traffic counting. So if we go out and we have some device that's capturing data across a highway network, we can derive the data that we would utilize for a secondary purpose. So these are the four kind of source types of data that we end up with, or ways that we can actually get data. It's sources. Then we also want to think about who produced the data. So a primary producer is going to be a researcher. The researcher sets up the data protocol, runs the model or the research, and gets data in a very primary way from that methodology. The secondary is when we utilize somebody else's data. We use a primary's data source, but we're not the one who originated the protocol, the methodology, or did the original data collection. We're just using the data. And tertiary is when we have derived data. So back to the highway counting analogy, we have counts, categories, or statistical results that result from a large data collection process, and that would be called tertiary data. Then under types of data, there's three main types. The first one is an index, or an ID number. Okay, it's some way to organize data. It's not really particularly meaningful in and of itself, but it can reference across many different databases and tabular data structures if we set up an ID number. And ID numbers are really important if we know that we're going to be having important data located across several different locations or in several different databases, and we know that we're going to want to relate some attributes to other attributes. Now, attribute type data is actually it's usually in a tabular format, and these are the things that pertain to what we're collecting. So for weather, it might be the dates of the calendar month, and for each one of the dates we have a actual temperature reading, and then we might have a column that says, is this cold, a nice day, or a really hot day? Those are all attributes of the data collection process. And then finally we have metadata, and metadata is just the data about the data. So that is usually held in an HTML page or in a PDF, a little text document. It's not the data itself, it's just describing what the data is for, maybe how it was collected, maybe some licensing, who can access the data, what's its main purpose. So again, it's not the data itself, it's just telling us some information about the data. And that's really important for GIS because oftentimes there's metadata characteristics that we can use very effectively for setting up our GIS analysis work. So oftentimes we want to know who collected the data, what's its spatial resolution, what type of map projection it's in, and oftentimes that's going to be in a metadata format. Okay, let's talk about the 4 ways that data is collected across categories. And this is important because we want to know once we get a data set, what's the measurement protocol. So we have 4 types, and let's walk through these. The first one's nominal. Nominal is just simply based on a name, so that's very qualitative. So you're either a boy or a girl in the image analogy to the right here. The second one is ordinal, and ordinal is when we're ranking something. You know, we're setting up. We have the raw data, and then we're going to order it in some way or rank it. The third one is interval, and the interval, the actual spaces between the collection buckets, we could say, are very important. So this is where we're actually very interested in the distance from start to endpoint within a particular section of the data. So oftentimes we'll call that interval. And then the last one is ratio. And with ratio, the start point of 0 is really important. So this oftentimes ratio will get a percentage, but we're starting from an absolute point, and 0 is a classic start point there. So these are the 4 ways that we'll see data and consume data. It'll be in this type of format. Regardless of all the characteristics that we just discussed, data is always sitting at the bottom of what we would call a knowledge pyramid. So data is utilized to produce information. Then to get to knowledge and wisdom, we actually have to utilize the information in a constructive, thoughtful way. And that's when we get into a decision-making process. And you'll oftentimes have multiple perspectives in a public decision-making process. And the best ones oftentimes are where many different perspectives can come together to produce a final result where every perspective is heard and weighted in equal measure. So we have sizes of data, so big data versus small data versus open data. And we want to talk about these real quickly because these are words that we hear quite often, but we might not really understand in detail. And if we have just some general idea of what these particular data types are, it's really very helpful to understanding where we got the data and what we can actually do with the data. So I'm going to play this little video. This is Rob Kitchen talking about open data and big data and what we would call the data revolution. And this is a really nice overview, very contemporary understanding of where we are in terms of data right now.
My name is Rob Kitchen and I'm a professor of geography at the National University of Ireland in Maynooth. Big data is a key part of the data revolution. So we now have this new form of data that is very large in volume, it's high in velocity, so there's a kind of continuous flow of it. It's very varied, it's interconnected, it's very fine-grained, and so on. But it's not the only part of the data revolution. We also have a big transformation towards open data and the sharing of data and on an open access basis. And we also have the formation of data infrastructures, which are these taken together, if you like, what we might call small data sets, traditional data sets, and then scaling them together into archives and repositories, and also again making them reusable and shareable and so on. There's no doubt there's a lot of hubris around big data, so there's a lot of kind of hype and speculation and so on, but at the same time there's a lot of justification for saying that this is actually a revolution, because it is changing the way that businesses operate, the governments manage and places. It's changing the way that organisations manage how they do their operations, and it's changing how science is practiced. But at the same time, there's kind of hubris in all of those bits. There's kind of overstatements of the benefits. And there's a lot of problems around big data. So technically, it's quite messy, it's quite dirty. It can often be quite difficult to analyse and to make sense of, and so on. And pronouncements like things like the end of theory, that's simply not true. You know, it certainly does lead to a change in how science is practiced, but it doesn't fundamentally alter the fact that there's kind of scientific principles underneath. You know, correlation is not, it doesn't supersede causation. You know, there is a lot of change happening, and on the other hand, we're still trying to work out what exactly that change is, and to, you know, separate out the hype and hubris from the actual real justification of what changes are really happening.
Okay. So, as Kitchen spoke here about big data particularly, we have what we would call 4 V's of big data. And let's go over those real quickly. So we have volume, which is the scale of the data. I mean, there's just so much data that's being produced at this point in time. And then we have a variety of data. So we have Facebook, we have tweets, we have YouTube, we have these big platforms now that are producing a very large scale of data, but they're producing it in a way that is variable. So the actual form of the data is not in a simple, easy to understand data table. It's just really complex data types. Then we have the velocity of the data. So a classic example is New York Stock Exchange trading. It's all digital primarily at this point in time, and we have 1 terabyte of trading information produced during each trading session at this point in time. So just the speed that the volume of data that's coming is quite great at this point in time. And then the veracity of the data is relatively low. So there's a big uncertainty of the data itself. And we really need to be careful about where we got the data that we're utilizing, you know, how much confidence is in the data, how much processing has been done on the data, is how raw is the data. And we need to be really suspect of the veracity of data at this point in time, because there's just so much of it. It's happening so fast, and it's in so many different types, in different varieties, that puts a lot of strain on the veracity and the housekeeping around data itself. At this point in time, we're housing this data also in physical structures on the face of the Earth, and those are becoming very large facilities. This is a national security site in Utah, and as you can see, it's very large, and this is housing server after server after server that's just devoted to collecting data. And we can see that this actually has a physical structure on the face of the Earth. So this is not something that's just, when we say the cloud actually does have a location, and it's usually in the server farm, and that's usually going to be sited on the face of the Earth. So we just need to be aware that as we increase our activity in terms of digital data, that data is showing up in an actual physical location. We also have what we call open data at this point in time. And open data is essentially a licensing format that allows for multiple uses of the data. Depending on how open the data license is, we can use it in many different ways or in very particular ways. But the big gain for open data is the fact that it is accessible, and it is something that we can utilize for purposes beyond maybe what the original data intent was, the original collection process intent was. And this becomes really exciting in the world of GIS because all of a sudden now we have access to a lot of data that we didn't have even several years ago, that we can combine with other data and produce really interesting, really meaningful results. So we can draw new correlations, we can discuss causation between new variables. We can just simply have machine access to a lot of data that we did not have in the past. And oftentimes this data can be accessed through APIs, and it can be very live 24/7 data that's constantly changing, feeding into interactive maps, which is very exciting. Part of the open data process is a willingness to be open, participation, and collaboration. So the open data communities that are alive and well right now, they traffic in the notion of transparency. That's a big component, and that's slightly different than data that would be considered to be closed or proprietary. Proprietary data oftentimes is not in an open framework, and it doesn't necessarily involve collaboration. It's just being collected by either one agency or one company, one corporation, and it may or may not be open and may be participatory. With open data, we basically have a 5-star development scheme, and this was coined by Tim Berners-Lee, what we would call the inventor of the World Wide Web, and his 5-star deployment scheme is really useful in understanding the benefits of open data. So let's talk through this for just a second. At the low end, if you were to just get a 1-star or a low ranking, you might be a PDF. And the issue with the PDF is that it's not particularly machine readable, and we can't easily get it into a tabular format that's machine readable. So it's there, we may be able to access it, but it's not very useful without a whole cleaning process on top of it. The second format is that the data's there, it's in a tabular format. It may be proprietary, it may be, say, an Excel format, and we're going to need something that can read an Excel document. The third type, the 3-star, would be a comma-separated value file that can be read across many different database structures and software that deals with tabular data, and that's a little bit more useful oftentimes than the Excel document alone, and very machine readable. And then the fourth type would be tabular data or some data structure that has a known web address that is opened through a URL, and we can see it and access it. And the best case scenario is the 5-star deployment scheme, where we have all those things that came before, but it's in a networked environment and it's really visible. So we know exactly where the data is, it's easy to access, it may have an API on it, so a machine can just pipe right into it and utilize the data. It's very accessible, it's in the right formats. A lot of care has been given over the idea that it can be used in an open data framework or in an open data environment. So we need to always think about, when we're dealing with data, how open is the data? How usable is the data? Do we have to do a lot of data cleaning on it? Do we have to get it into a format that's machine readable? How friendly is the data? And we get a 5-star if it's super friendly, and if it's really unfriendly and needs a lot of help and a lot of cleaning, it's probably going to only get 1 star. So let's talk about data in a spatial framework, what we might call GeoData, and specifically the raster model. So with the raster model, we are cell-based at this point. So we're getting rid of the model that vector traffics in, which is points, lines, and polygons and connections between those things. And we're getting into a cell-based structure. And we can see our little kitty cat here, and he's obviously a GIF. He's a raster-based thing. And we derive meaning from the image because we look at it and we see a funny little cat waving its hand, and that's, you know, humorous to us, and so we derive a certain meaning from it. But at its core level, it's just a series of cells that are in a pixel format, and they have different values, and the different values represent the purple to the white color to the dark brown color. So we can think about this particular image, or this little kitty cat, as being a raster format, and it only has meaning in a certain context. It's not really helpful in terms of GIS. So with GIS, we really need rasters that have features that have 5 things usually. So the first thing is that it is not a part of the vector model. It's completely separate because it is raster based. And second, it is cell structure, so each one of those pixels or grids, that's its own entity, and it's basically a cell. And those cells, the spatial resolution, which I'll explain in a second, is really important. And the values in the cell structure can either be continuous values or discrete values, and I'm going to talk about what that is in a second. And finally, it's either going to be thematic in nature, or it's going to be what we call a multi-band product, and I'm going to explain what that is also in just a second. So the raster model features these 5 kind of characteristics, we could say. First thing, it's not a vector. So if we look at the vector format, on the left-hand side we see essentially a polygon that may be a lake, and on the right-hand side we have the raster format. And they're representing the same feature, they're just doing it 2 different ways, the feature being the lake. So with vector format we get a nice smooth edge, which could be really useful. We might get some attributes behind it that pertain to the particular lake. Maybe who owns the lake, what's the square area of the lake, does it allow fishing or not, what type of fish are in the lake. In the raster format, all we have in the raster format is a cell, and the cell just says, I'm this kind of light blue color, and that light blue color represents water as opposed to a feature around it. So the attribute structure is much less developed, but what's important is that we have cells now that represent that lake. And each one of those cells that's a lake cell, it's the same value as the cell sitting right next to it. And a cell is essentially the unit within a row and a column. And for geospatial rasters, we oftentimes are sensing the Earth's surface, and as we do that we have different features, and the different features can be represented by cells. So in this case, if we look up at the left-hand image, we can see that it looks like houses, there's a little road and a river, and if we zoom into it on the right-hand side, we can see that the area right next to the river, that's a dark green color. And we can see those cells, they all basically have the same color. Thus, we can assume they have the same value, the same number that's sitting within the cell there, versus the street and the house, or the rooftops and the river itself. Those have different values. We have spatial resolution in images that we use, or rasters that we use in GIS. And a high spatial resolution image has a finer network of cells, we could say, and a low one has the cells are actually larger. And what's important to realize is that high versus low is not a value judgment per se. One's not better than the other. We're just going to use low versus high in different contexts for different purposes. So let's think about this for a second here. if we have on the left-hand side, a relatively low spatial resolution image at 30 meters versus a relatively high resolution image at 4 meters, we can do different things with these two rasters. So 30 meter is usually considered to be relatively high resolution when we're talking about satellite imagery. It's kind of low when we're talking about what we would call an orthophoto or a flyover photo. When we mount a camera on top of an airplane or on the bottom side of an airplane, we're usually getting really high resolution imagery where the spatial resolution, its fidelity with the actual sensed Earth surface, is really high, where we can really make out people, roads, cars, individual items in the landscape, because it's being collected at a really high resolution, in this case 4 meters, versus 30 meters where the cell size is literally 30 meters across in one direction, the width, versus 30 meters down in terms of height. So cells are always the same, or usually they're the same height versus the same width, and that distance, that kind of square area in the cell, is defined by its height and its width. And we just can simply measure across from one side to the other side of the cell, and that'll give us a sense of how big that image is, or how big the cell is. In this case, it's 30 meters versus 4 meters on the right-hand side. We also have continuous versus discrete rasters. So on the left-hand side, this is a classic digital elevation model that just has a high value versus a low value, and there is a sequence between the highs and the lows that's continuous. Okay, so we might have lots of 1s, 2s, 3s, 4, 5s, all the way on up to a high value. And what's important is that it's like surfaces that we experience on the face of the Earth. It's continuous in nature. It's kind of flowing. All the values represent flows from one location to another location within the raster space. Now, discrete is usually when we have put some type of meaning on top of that continuous data. So in this case, we might want to group the data into certain breaks. We're looking at the same image as the one on the left-hand side. So we can see that there's some yellow areas. Those yellow areas are the areas where the DEM raster is very low elevation, where the value is very low, versus the blue versus the purple color. And we've just had a GIS put on top of the original continuous cells what we would call discrete values, or values where there's a definite break in the continuous nature of the data set. And there's reasons why we want to have discrete rasters, which I'll describe in just a second. So with continuous raster data, all we have is just from a high to a low, and it has this kind of flowing nature. So here we're kind of looking at what might be considered a elevation raster. So the dark green areas, those are real low elevations, and then the red would be a high elevation area. And we can see it's kind of like little steps. It's continuous in nature. And oftentimes the cell right next to the one adjacent to it is very similar in value. When we get these rapid changes in value, that's where we get a change in the landscape oftentimes, or in this case, in terms of elevation, where a slope would be really steep. Now that's very different than what we would call a discrete raster. Now in a discrete raster, what's happening is we still have the same cells in the same location of the cells, but we're clumping or grouping at this point in time cells of like values. So in this case, we can see that we have blues versus reds versus yellows. And oftentimes we'll do this with land use, where we want to say here's an urban area versus a forested area versus a water body versus open space. We want to give some meaning to cells of a like value. There's a reason that we want to clump the cells together. They might not necessarily be the exact same value, but they're close enough to be considered a meaningful feature in our data set. So here's kind of a good example here, where we might have a raster that deals with vegetative cover. In the types of vegetation, we can group into walnut trees versus cottonwood, aspens, junipers, and firs. And we can represent in the raster a value for each one of those types of trees. And we can then give it a code, and it acts a little bit like a vector attribute table. And we can actually make an attribute table out of those discrete cell values if we want to. So again, discrete, we're putting some type of meaning on top of continuous values, and we're clumping or grouping the raster values into meaningful categories or meaningful breaks. There's 6 main types of rasters that we deal with on an ongoing basis. The first one would be orthophoto. Second, land use, concentration, slope, elevation, and population. 5 of these are what we would call thematic rasters, and the one that's kind of the oddball here would be the orthophoto. So with the orthophoto, this is what we call a multi-band product. The other ones, land use, concentration, slope, elevation, and population, those are usually what we call a single band raster or a thematic raster. They just have one layer of cells, and those cells thematically represent what's being collected, or the whole data point of the actual raster itself. So again, we might have a land use raster versus population density versus DEM, which is elevation. In the orthophoto, what we're doing in that case is we're stringing together 3 different bands of cell values, and these are being collected across what we call the electromagnetic spectrum. So in band 1 we might have reds, band 2 we might have blues, and band 3 we might have greens. And oftentimes this is what it will look like in a GIS. So if you drop in a raster and you see under the raster name a band 1, a band 2, and a band 3, and those are represented by red, green, and blue, you have a multi-band raster on your hand. And it'll oftentimes look like the image that we see here, what we would call true color. And again, this is not a thematic raster in and of itself. It's a multi-banded product. Now that's very different than a raster that we put into GIS, and then when we just see a high value versus a low value, and that particular value just represents some thematic that's being collected in terms of data. So in this case, it's DEM, digital elevation, and the reds in this case are low points, and the greens in this case are high points. And if we kind of look at it, it looks like the reds are probably maybe in a river, in a watershed, and those are river areas, and then we might get into high terrain or mountainous areas where there's green values. So this brings us to the end of class 5, and we've discussed what we would call geodata, or data within a spatial framework. We use that for GIS, and the raster model is very important. We've done some work so far in vector, and now we'll be starting to utilize rasters on a more ongoing basis going forward in the class. And we've also discussed the different characteristics and types of data in general, and those all are very applicable to thinking about data within GIS.